Newton didn't invent modern physics in a single afternoon under an apple tree. His actual work was a lifelong process of absorbing and refining centuries of existing, often contradictory knowledge. He was a master synthesizer. He spent years immersing himself in everything available to him, from the classical works of the ancient Greeks to the latest breakthroughs of his own contemporaries. The first track was pure mathematics. Newton studied ancient Greek geometry, specifically the foundations laid by Euclid and Archimedes' methods for calculating areas and volumes. He then integrated the work of modern thinkers like René Descartes, who advanced analytic geometry, and François Viète, who pioneered the use of symbolic algebra. But even with these tools, math remained fragmented. Geometry and algebra were isolated disciplines that produced static rules. They lacked a language to describe a universe in constant dynamic motion. While Newton mastered the math of the page, a second track of knowledge was evolving in the physical world. Before his work, humanity had a deeply fractured understanding of how objects actually moved. On Earth, Galileo had established the principle of inertia. He observed that an object will continue moving in a straight line unless a specific force acts upon it. But the heavens seem to follow different rules. Using the precise astronomical data of Tycho Brahe, Johannes Kepler realized that planets travel in elliptical orbits, not straight lines. This created a massive scientific tension. 17th-century thinkers treated the physical laws governing objects on Earth as an entirely separate system from the laws governing the planets. Science was siloed into isolated blocks. Humanity lacked a universal mechanism to connect the static geometry of a diagram to the motion of a falling object, or the path of a planet in deep space. Newton was driven by a relentless curiosity to decode these patterns. He saw a changing curve on a page and a planet orbiting the sun as the same problem. They were both systems defined by constant change. He began his synthesis by hacking together the approximations of Archimedes, the geometric proofs of Euclid, and the algebra of Descartes. This fusion resulted in the invention of calculus. It was a radically new mathematical language designed specifically to measure and predict objects in flux. Once he had a way to calculate change, he applied this logic to the disconnected physics of Galileo and Kepler. This led to his universal laws of motion and gravitation, which he published in the Principia Mathematica. This was a profound conceptual leap. Newton proved that the gravity pulling an apple to the ground is governed by the exact same physical law that holds a planet in its majestic orbit. This obsession with decoding complex natural patterns extended beyond motion. Newton applied the same rigor to the study of light. In his famous prism experiment, he passed a single beam of white sunlight through a glass prism and watched it fan out into a rainbow of distinct colors. He deduced that white light is not a pure, singular element. Instead, it is a hidden combination of different wavelengths, each bending at a slightly different angle. This observation stripped away the assumption that light is simple. It proved that even the most basic natural phenomena are built from specific, hidden components working in unison. Newton's ability to unify centuries of past data became the direct blueprint for classical mechanics and the modern scientific method. Today, we use this exact logic in spectroscopy. This graph shows light data from interstellar space, analyzed based on Newton's insight that light splits into components. By identifying these specific spectral lines, the sharp dips, scientists determine the chemical signatures of stars and distant galaxies. We see it in the laser as well, a tool that functions by isolating and controlling light's specific wavelengths with extreme precision. None of these modern miracles stem from a single, isolated moment of genius. Newton's legacy is that he stood on the shoulders of giants. He relentlessly cross-referenced ancient texts and contemporary data until they fit together into a single system. Scientific breakthroughs are rarely spontaneous. They are the result of a mind capable of identifying how centuries of fragmented data actually function as parts of a single, coherent reality.